9.5 is looking over what electrolytic cells are, and then 19.2 finishes off topic 9 with actually electrolysis, what we use electrolytic cells for. Now, key differences. We've been working with and talking about voltaic cells up to this point. So keep in mind, voltaic cells, they take energy from spontaneous redox reactions and harness it to produce an electric charge. So we can create a charge from that. Well, electrolytic cells differ in the fact that they use an external source of voltage to run a non-spontaneous redox reaction. So this allows us to go in a reverse direction if that is the product in which we want, whereas voltaic cells will only move towards the spontaneous direction. Some key terms about electrolytic cells that are different from voltaic cells are the electrolyte. The electrolyte is the solution that the electrodes are submerged in. And this is really where the reactants are in the process. So in a voltaic cell, the electrodes were essentially your reactants. Here, it's what is in the electrolyte that we care about. What's in that electrolyte could either be a molten ionic compound or a solution of an ionic compound. It all depends on what we are trying to pull or separate in that ionic compound. How the process works. We use an electric current. We pass that electric current through the electrolyte. In the electrolyte, this is where redox reactions occur, and they occur at the electrodes. So we still have a cathode, we still have an anode, based on two metals submerged within the solution. This electric current is going to remove the charges of the ions in the electrolyte at the appropriate electrode. And this ultimate process creates neutral elements. So the whole purpose behind an electrolytic cell is separating important reactive metals from their ores, or just separating metals from ores themselves. And so understanding that most of our pure metals aren't pure in nature, they are with other ions, we have to use this process and use electricity to separate them based off the charges in which they carry. Here is a generalized picture of what an electrolytic cell looks like. It's different in that fact that a voltaic cell has two half cells. This one is just one electrolytic cell. Some key areas to look at. So we still have our glass beaker. Within there we have our electrolyte. So our electrolyte is that molten salt or ionic solution that we're looking at. We have two inert electrodes. These can just be a metal, an inert metal, or a process in which that's not going to take part in the process. Now, our inert metals are attached to an external wire, just like in a voltaic cell. But what's different is this portion right here. In the voltaic cell, we said this was a voltage. That's our voltmeter to read the electron flow. Here is where the source of power is going to come from. It can either be a battery or a direct current or DC current. It is represented in a very specific manner where the positive ode is the longer line and the shorter line is the negative or the anode of the battery or the device supplying your DC current. All right, so what's going on in the solution itself? We have our anions depending on what solution it is. Those anions are going to move onto the inert metal. Hence, your anions are going to be oxidized. We are going to pass those electrons up and over the wire to the power source. The power source is going to be the one giving off electrons to the cathode. And that cathode is therefore getting an overall negative charge, accepting your cations onto the metal itself, and you're going to get cation reduction occurring. So this way, we are actually pulling out of solution both cations and both anions, and we're going to see an example of this later on with actual chemical compounds. Make sure when you're making this drawing and you're making it correctly, or if you're describing how an electrolytic cell is set up, you're using the proper terminology and sources. You need to represent your source of power. So that is going to be that long line and short line parallel to each other. You need to make sure that your electrodes are immersed in the solution or the electrolyte and connected to those external wires. And then those external wires are connected to that power supply that you're representing. Okay, so what's going to happen here is the power source pushes electrons to the cathode. And this is why you see this negative charge on the cathode. When you think, well, the cathode's positive, why is there a negative sign there? Well, that's because the electrons are being pushed to the cathode. So now the cathode inert metal becomes negatively charged so that it can attract your cations. Well, now this causes your cations to become neutralized and go to their natural state, or the state in which they're going to be in. Your anions migrate to the anode. This is what is actually creating the electric charge or the electricity in an electrolytic cell. In a voltaic cell, the electric charge comes directly from the transfer of electrons from one cell to the next. Here, it is the movement of cations and anions to their cathode and anode that produce the electric current. Because the anions migrate to the anode, that anode has become positive because electrons are leaving, going back to the battery source. So those anions donate electrons, they become neutralized and go back to their natural state, and the electrons return to the power source to be used and pushed towards the cathode again. So that external power source is the supply of electrons for this particular electrolytic cell versus the voltaic cell where we're creating ions, and that is what's providing the electrons. All right, so redox reactions occur at the electrodes, just like in a voltaic cell. An electrolytic cell, same thing. It's just the charges that are created at either is different. So the negative electrode in an electrolytic cell is your cathode. That is where reduction occurs. So your positive cation is going to accept the electrons from the cathode to create your neutral ion or neutral element. The positive electrode is your anode because your negative ion is going to donate an electron and create the neutral compound so that electron can go back to the power source. And this is where oxidation occurs. Now, keep in mind, the nature of the redox reaction defines the electrode, not the electrical charge. So in a voltaic cell, oxidation occurred at the anode, but that created the negative charge. In the electrolytic cell, oxidation still occurs at the anode, but is it a positive charge because of where electrons are being pulled from and moving to? For the cathode in a voltaic cell, it is still a reduction reaction, but it carries that positive charge as the electrons are being dispensed. In an electrolytic cell, reduction still occurs at the cathode, but it has an overall negative charge as that's where the electrons are moving to. So even though they have opposite charges based on the diagram in which you're going to represent, oxidation still occurs at the anode for both voltaic and electrolytic cells, and reduction occurs at the cathode. All right, so what are we going to use from this? Well, predicting the products in electrolytic cells. How do we know what we are going to make in this process? Steps you want to do. First, you want to identify all the ions in your electrolyte, what is provided to you. Once you know what's in your electrolyte, you want to determine the ion migration. Which ions are going to the cathode, which ions are going to the anode. What if there's more than one ion in that solution? Well, the discharge, and that means loss or gain of electrons, movement of electrons, is based off their standard electrode potential value from table 14. We'll talk about that a little bit more in one of our examples. Then you're going to want to write your half equation for each electrode. Remember, at the anode, that is where oxidation is going to occur. The cathode is where reduction is going to occur. So make sure you are putting the appropriate ions at their appropriate electrode. Then you want to balance your electrons that are lost and gained in order to write your net reaction. And then consider what changes could be observed throughout this process so you know a reaction is actually taking place. First, we're going to look at the electrolysis of molten salts. In 19.2, we're going to look at a little bit more details of electrolysis taking place in other solutions, aqueous solutions versus molten salts. 9.5, the SL stops at the electrolysis of molten salts. So keep that in mind as we move forward. So what makes a molten salt unique? Well, only ions present in the compound and the electrolyte itself is the compound itself. So it's very easy to determine which ions are going where. It's when they're in that aqueous solution does it get a little bit tricky, and you have to figure out which ion's going to go where and which one has more of reduction or oxidation power over the other ions in that solution. And that is in 19.2. All right, so we are going to do an example, a couple of examples of representing what goes on here. So the first example we're going to do says, describe the reactions that occur at the two electrodes during the electrolysis of molten lead bromide. Write an equation for the overall reaction and comment on any likely changes that would be observed. All right, our example. Step 1. Deduce the ions present in the electrolyte and to which electrode they will be attracted to. So we know we're working with molten lead bromide. So we're working with Pb, Br2 in a liquid state. This is going to dissociate because it's molten and it's liquid into Pb ions and your bromine ions. All right, so now we want to determine which electrode they go to. Well, first look at lead. Lead has a 2+ charge. It's going to be accepting electrons to create a neutral compound. Therefore, it's going to be reduced. That means it's going to be moving to the cathode. Bromine has a negative charge, so that means it has electrons in which to donate. Because it has electrons to donate, it's going to be oxidized in order to get it back to its standard state. Therefore, it is going to move to your anode. All right, so we have identified what our ions are, and we have identified which electrode they're going to go to. So now we want to write our appropriate half reactions. So at the anode, we are going to have bromine. So bromine is being oxidized. So that means it's going to be losing electrons. We have, in our standard state, bromine is a Brinkelhoff, so Br2. And it is going to be releasing 2 electrons, 1 per bromine. And this is representing our oxidation. At the cathode, we are going to have lead moving towards there. Lead is going to be accepting electrons, 2 of them, in order to balance its charge. And that's going to create lead in its standard, or in its neutral state. Now that we have identified the half reactions, we can write our net reaction. And that means we can go through and cancel out our 2 electrons because they are the same on either side of that reaction. Luckily, our electrons are balanced here. If the electrons were not balanced, you would need to balance the electrons so that they cancel out appropriately. So now that we have done that, we can write our net reaction. So we have our lead ion reacting with our bromine ions to create lead and our bromine in their in their individual states. Observable changes that could have occurred. Well, because bromine is being pulled out of solution, we know there's going to be that brown liquid, and there's going to be a smell that is tied to bromine. At the cathode, as lead is being pulled out of solution, you're going to start to see a little bit of gray precipitate at the electrode at the cathode, representing the lead that is being pulled out. Then we can filter it, and we now have pure lead for any purposes we may have in industry. All right, so a problem with the process of using molten salts, which is the ideal process because we can guarantee the two ions we're going to pull out. So this is really important for especially precious metals that there's not a lot of. But one of the biggest problems is the high melting point of salts. So because of the high melting point and the high temperatures in which these have to run, it is very costly to generate and maintain the process, especially for industry. Therefore, what they have found is you can mix two salts together. One of the salts is going to have a lower melting point than the other. Therefore, when they mix, it lowers the melting point of the higher one, and that makes it more economical. You always want to choose a salt with a lower electrode potential value than the one you're trying to identify so that it does not interfere with your calculations. And we're going to do an example of what does this look like and how do you know. So give you an example. If we want to pull sodium and chlorine apart, sodium chloride, the salt, has a melting point of 801 degrees Celsius. Therefore, we mix it with calcium chloride to bring the melting point down to 580 degrees Celsius. That is significantly lower, which makes it more economically feasible. Why did we choose calcium chloride? Well, if you look in table 14, you would see that calcium chloride, or calcium, sorry, not calcium chloride, but calcium itself. Calcium has an electrode potential of negative 2.87 volts, whereas sodium has an electrode potential of negative 2.71 volts. That means because sodium is the more positive value, it is more likely to be reduced. So it's going back to table 14 and understanding who's higher on the reactivity series. Because calcium's more reactive, it wants to stay in solution. So it's not going to be affected by this whole process. So even though we have a solution of calcium chloride with sodium chloride, you can determine that sodium chloride, or sodium specifically, is going to be the element pulled out of solution because it has a higher reduction value or it's less reactive. So that way we know we're going to get sodium in this process. So we can do the same thing that we did previously of identifying which one's going to the cathode, which one's going to the anode, and writing a net reaction from there. So we have sodium chloride in its liquid state because it's been put into its molten state with the help of calcium chloride. In its molten state, you have sodium ions and you have your chlorine ions. Because sodium is your positive ion, it's going to go to the cathode. Because it's going to accept the electrons, and chlorine, because it's negative, is going to go to your anode. So now that we have identified what's going where, we can write our appropriate half reactions. So at the anode, we have chlorine. Chlorine is going to be oxidized, and therefore it is going to be giving off electrons. It's going to give off 2 electrons because chlorine is a Brinkelhoff, therefore we need to account for both of those electrons. What's going on at the cathode? You have sodium. Sodium is going to accept an electron to go back to its neutral state. But because chlorine has 2 electrons that it's giving up, sodium needs to be able to accept 2 electrons. So we need to make sure we balance the number of electrons through the reaction. So now we can cancel out those electrons and we can write a net reaction. So we have 2 sodium ions reacting with 2 chlorine ions, and at each electrode we're going to have sodium and we're going to have chlorine gas, because it's in its gaseous state, its natural state. And then we, of course, would be able to pull sodium out of solution when we solidify it. What are observed changes? Well, because chlorine is a gas in its natural state, we're going to see bubbling at the anode. And because of sodium, we're going to start to see sodium collect, and you're going to see a silver precipitate, essentially, at the electrode for the cathode side. All right, so what we can do in addition to this is, using sodium chloride, draw an appropriate electrolytic cell showing what's happening with the molten salt. All right, so here we have our cell. We have our 2 inert electrodes. I'm going to connect those inert electrodes to a power supply. Remember, the long one is positive, the short one is negative. I'm going to identify what's my anode and cathode. Our anode is hooked to the positive side of our power supply, and it does carry a positive charge. The cathode is connected to the negative side of our power supply, and so that metal carries a negative charge. Then we have our molten solution. So here we have the molten salt, sodium chloride. So what is going to happen because we have this occurring? Well, we have Na, and we know Na is going to get attracted to the negatives on the cathode. So sodium is going to move to the cathode, and it's going to accept those electrons to become a neutral sodium element. And then we have chlorine. Because the electrons are being pulled from this metal to the power supply, it's gaining a positive charge overall. So that means this chlorine is going to donate its electrons to create the electrons needed to go back to the power supply and sort of neutralize that electrode. And as a product, we're going to get the chlorine gas that bubbles off. And so this is a way in which to represent what's going on with actual ions and deciding where the ions go. The last bit of information we have left out is flow of electrons. So the flows of electrons, because electrons are negative, will always flow towards the positive. And then on the cathode side, towards the metal, the positive ion, in order to neutralize the appropriate atoms.